So today I will try to persuade you that we can actually make sense of solid-state fusion with known laws of physics. I will start with maybe a change of the point of view in which we can see nuclear fusion, and I will argue that we can see nuclear fusion indeed as a nuclear decay. And if we accept this point of view, basically the goal of this community might be seen as creating the condition to make this decay faster. And so to do so, I will present you two options. There can be also others. Option A is going to be more like a historical review of the screening, but John just did it very well, so I'll go fast. And the second option is actually where we are really working on, which is like studying how nuclear excitation transfer can accelerate this nuclear decay. And finally, I will share with you our roadmap for the future. But first, let me acknowledge the people who did most of the work. So first is Peter. He's professor at MIT, and he really pioneered this idea of excitation transfer, and he's working on it since many years. Then there's Florian, who presented yesterday. He is a research scientist at MIT, working with Peter in theory and experiments. And then there's me. I'm actually a postdoc based in Zurich, working more in biophysics, but I'm working with them as a research affiliate at MIT in these topics. So let's then start indeed with this change in perspective. Imagine that we have a gas bottle of deuterium, like at high pressure, so it might contain something in the order of 10 to the power of 25 molecules. So each molecule, we know it's composed by electrons and the nuclei of deuterium. And clearly, and the distance, the average distance between the two nuclei is in the order of 0.74 Armstrong. And that's like a sketch of what we can think of the potential energy between the two due to the Coulomb repulsion, due to the Coulomb force and then the nuclear force. So we are talking about a quantum system, and therefore we cannot get rid of tunneling. Tunneling is always present. And so we can calculate like a probability of such a tunneling in this system. And this was actually calculated already in 1989 by Koenig and Naumburg. And this probability actually is non-zero, but still very close to zero. And indeed, it provides like a lifetime of the reaction, which is astronomically large, but still not infinite. So it's 10 to the power 57 years. So to give you like an order of magnitude of what this means is that even just to wait for one reaction, like for one fusion reaction in that bottle, you should wait like something like 10 to the power of 40 years, which is much longer than the age of the universe. So by all means, this probably never happened in our universe. But anyway, we have like a law, and so even though it's ridiculously small, we would like to try to see whether we can speed up this process by a lot, of course. So the goal of, let's say, the field of fusion, nuclear fusion, is to try to make this decay faster. And so one way to do that, we know it, is that we can heat up the system, and that's basically what plasma fusion does. You make the particle more energetic, and we know that works. It's just that, at the moment there are clearly technical limitations to get energy out of it. And then there is, let's say, our approach, which is the idea that we can have fusion in the solid state. So in principle, having more confinement of the deuteron in the solid state. So let's investigate this system, and specifically with these two approaches to speed up the reaction, the nuclear decay. So as I said, we can think of the tunneling, and we can really do some simple maths with the Gamow model. And the idea now is, instead of providing more energy, like what plasma physicists do in tokamaks, etc., we want to change the potential energy. And we used to do so by loading this deuterium in palladium, for instance. And the idea is that if we can have like a molecule of deuterium, this is actually still debated, but there are some calculations, some theory that they're quite confident that that is possible. We have this molecule of deuterium embedded in the lattice, with, of course, like a sea of electrons due to the lattice itself. And therefore, there will be some more screening, and so the molecule will be a little bit more compact. At least some studied report proposed that. And not by a little bit, by quite a lot, like 20%. And as John also discussed, this nuclei can explore like a distribution of position. And this would further decrease, actually, the lifetime of the fusion reaction of just a deuterium molecule in a lattice. So summarizing this first part, the metal lattice can accelerate, like optimistically, up to 30 orders of magnitude, the D2 decay in the lattice. So if we look at it like in log scale, because otherwise you cannot really appreciate what's going on, the black line is what we would expect in terms of nuclear decay for a molecule in a gas bottle. And the red line is what we can expect, like just by having screening effects of a molecule in a lattice. The problem is that our target is still far away, because for observable effects, there's still like a big gap. I mean, we can discuss what we mean by observable, but by all means, there is still like several of those orders of magnitude of gap. So we now focus on this last step by describing you what excitation transfer is. And I will really try to go step by step, so maybe I will not be extremely precise in terms of the formalism, but just to give you insights in what excitation transfer is. And I will try to explain you this concept with like 4 lessons. One, starting with some mechanical analogs that can, let's say, give an interesting, that are analog to what happens at the quantum scale. Then moving to the molecular scale, there is actually a technology that works, that many labs around the world use on a daily basis. For instance, what I do in Zurich is about that. Then we will translate these ideas to the nuclear level, and then finally apply to deuterium. Let's start with lesson 1. So, and by the way, this is not things that we develop, but there's actually plenty of literature that performed this, that did study these analogs to quantum mechanics. So imagine we have a pendulum, so pretty simple system, and at the bottom we see the graph of the total energy of the pendulum. So kinetic plus potential energy. This is a damped pendulum, so the energy slightly decreases over time. Now imagine we have 2 pendula, and the blue one in this case is not excited, while the orange one is excited. We put it out of equilibrium. And we also attach like an elastic string between the 2. So a weak coupling between the 2. And let's see what happens to the energy. So we see that basically the excitation that originally was in the orange pendulum is at some point of time transferred to the blue one, and then it's transferred back. So there is some sort of periodicity in such an excitation. And what happens if we increase the coupling, so we put like a stronger spring, let's say, between the two oscillators, we observe that this frequency of exchange is even faster. So that's basically the conclusion of this first part. If we have a coupling, we can have this exchange of energy between two oscillators. So let's see now, step 2, molecular world. Imagine now we have two molecules. These are fluorophores, usually artificially designed molecules that can get excited at a specific wavelength, like green or red photons, and then emit a photon of a similar wavelength. In this case, the energy is plotted on the y-axis, on the vertical axis, and are in the order of electron volts. So we excite with like green laser light or green light, and the green fluorophore get excited. So that's an excitation of the electrons. If there was no red photon around, or sorry, red fluorophore around, what would happen is that this would emit like a green photon. But since we put in our system a red fluorophore nearby, and there is a dipole-dipole coupling, this is usually the coupling that there is between fluorophores, the energy can go, actually switch basically between the green fluorophore and the red fluorophore. And now what we have out is a red photon instead of a green photon. This is analogous to what I was showing you before, except that we are simply stopping the system like there, midway, and we have an excitation out. So from the molecular perspective, we learned that we need a coupling. In this case, it's a dipole-dipole coupling, so electromagnetic coupling. And second is really important that the green fluorophore, thanks to this other channel of the excitation, can decay faster than it would do if it were isolated. Lesson 3. We move to the nuclear level now. So imagine now, instead of the two fluorophores, we have two nuclei. And here I picked two nuclei of iron-57, which is an isotope widely used in nuclear science. In this case, the energy involved are in the order of kilo-electron volts, so 10,000 times actually higher than the previous case, but still the analogy holds. These are nuclei, so they can get excited also in terms of the nuclear excitation and not the electronic excitation. So if we have like a free electron laser, we can excite these with highly energetic photons. And so imagine we have the excitation of one of the two. If there is a coupling, what can happen is that the excitation can be transferred to a nearby nucleus. And in practice, then we can have the photon emitted out of another nucleus. Actually, what can happen in this particular case, that since the two systems are resonant, so they can get excited with the same energy, they can actually go back and forth before actually finally emitting a photon. So that's analogous to the case of the two pendula that can show some like oscillations before like the actual emission of the excitation through a photon. So, is the picture that I just showed you just a picture, or does it really happen in reality? So we know that the coupling that I showed you can exist. That can be magnetic coupling, actually, or also coupling of other form. And then let's ask the question, do we have experimental evidence of what I just showed you? So like a mechanism that can make a decay faster at the nuclear level? And the answer is almost. We have two very interesting papers published recently that I will now describe to you briefly, that we think are really in the right direction, but they are not like closing the circle around it yet. So the first paper demonstrates that there can be excitation transfer between nuclei, but without, strictly speaking, a direct coupling between the nuclei. And this is by Haber et al. 2017. And now, actually, I'm a bit simplifying the experiment because it's a bit complicated, but the idea is that we have two layers of iron-57 into two cavities, optical cavities, and the iron-57s are coupled to the cavities, and then the two cavities are coupled together. And what you can do is that you can excite one layer, and then the excitation can go to the other layer. So this is nuclear excitation of the iron-57. And then can go back. So they can oscillate. The problem here, as I told you, is that there is not a direct coupling between the nuclei. The coupling is mediated by the cavities. So let's now move on in an experiment where there is a direct coupling between nuclei. And in this particular case, they observe faster decay. So faster nuclear decay. It's by work by Chumakov and colleagues. And also here I'm a bit oversimplifying, but the insights are correct. So now we have a crystal of iron-57. And again, with a free electron laser, you can excite, for instance, two nuclei at the same time. And they form like a coherent state, like a Dickey state. And what happens is that what we see like in the center, that's the exponential decay of the nuclei. If we excite 5 at the same time, the decay is faster. So the first photon emission happens at a shorter time scale. If you excite 10, it's even faster. If you excite 20, even faster. There is a linear relationship between the number of excited nuclei and the emission of the first photon of the ensemble. That's due to Dickey superradiance. That's a known effect. But this paper, to me, is really remarkable because that's really the first demonstration that this superradiance happens at the nuclear scale. But it's even more remarkable because it demonstrates how this superradiant effect are due to a coupling, like intrinsic between the molecules, between the nuclei, due to magnetic coupling. So let's try to push it to another level. That is, really try to link the idea of having the coupling that allows an energy transfer. And for this, Peter developed a model, and we are preparing a paper that will report about this model that shows how this is possible, again, using these delocalized states, these Dickey states. And in practice, what one of the goals of the paper is also to show practically how a variation of the Chumakov experiment performed under oscillating electric field might lead to really a proof of this model that we are developing. So let's then change gears finally to the deuterium. So in this case, imagine we have our beloved lattice of palladium, for instance, and a deuterium molecule and an helium atom nearby. Now, the energies are in the order of mega electron volts. And here there is a critical thing that probably needs to be digested a little bit if you are not already familiar with it. And this is the idea that a deuterium molecule can be thought as an excited state of a helium atom. It's like an helium atom plus 24 mega electron volt. So if we can create a coupling between the two, in principle, what we could observe is that the deuterium molecule might fuse and the helium atom might fizz. What's the problem here? The problem is that first, this process would be also very, very slow, like extremely slow. So how to make it faster? Well, through superradiance, for instance, through collective effects. Like in the Chumakov paper that I showed you that demonstrates experimentally that you can couple together nuclear states and having them decay faster. The idea now is that if we have plenty of molecules, like of deuterium molecules in the lattice, coupled together now, we can speed up the process thanks to this decay enhancement factors that are usually linear or let's say at the little power of n, so they really scales with n. And so what could happen now is that we might have, let's say, this exchange with one helium atom having it excited and one deuterium molecule fusing. What's the problem here is that clearly the system will remain closed because, okay, we are gaining a fusion, but we are also subtracting 24 MeV for the fission. So this little system that I just showed you would be analogous to the two pendula that simply goes together, goes forever without never really emitting energy. So what's then the potential solution for that? The idea is now that if instead of coupling to a helium atom, we could couple with an heavy nucleus in the lattice that has excited states at the same level of like a helium atom or deuterium molecule, so like 24 mega electron volts. And if we are able to create a coupling between this delocalized state of deuterium molecules and a helium atom, all inside the lattice, we can get the heavy nucleus to get excited. And since usually a heavy nucleus excited can decay fast, usually, they're not very stable, we can now truly have the energy out of from a fusion event combined probably with a fission event in this specific model, for instance. So to conclude, but Peter will give tomorrow a more technical talk about this mechanism with some recent advancements. But the idea is that, for instance, we envision that one possible heavy nucleus, target heavy nucleus to work might be tungsten. That might collect the energy of a fusion event of deuterium and then fizz, so like emitting an alpha particle and becoming a hafnium. And of course, there are some calculations attached to it. So we can see now that screening plus excitation transfer that are absolutely not mutually exclusive, but they can sum up, might lead to an exponential decay increase, like a faster exponential speed up of the D2 decay from D2 in a gas bottle, that's the black line, to D2 just in a metal lattice with screening. That was our target, the green dashed line. And the screening plus the coherent effect might really help to do this last step in this reaction, making it faster. So with that, let me just share our roadmap for the future. So we think that the theory is relatively under control, although there still needs to be some work to be done, probably with some postdocs. From the experimental side, instead, I identified 3 milestones that probably needs to be accomplished really to get to the proof of principle that we are really looking for. So milestone 1 is more about to show, experimentally demonstrate that there can be a structure like a D2 molecule really inside the lattice. So far, there's only like a theoretical evidence, but not really an experiment that shows that. And of course, it's very difficult to do it. Second would be to show that there can be non-radiative excitation transfer between nuclei with coupling, like a sort of direct coupling between them. And milestone 3, in our opinion, that would really be like the proof of principle experiment, is to show that there can be non-radiative excitation transfer between an excited D2 molecule to an acceptor nucleus. And so probably we might think of some nuclear products that might result thanks to this, to the theory that Peter will explain you tomorrow. And with that, I'm done, and I'm happy to take questions if there are any.
Hi, Ross Koningstein, Google. I love the nuclear excitation angle.
Me too.
So on milestone 2, which reminds me a little bit of Mossbauer spectroscopy, you end up having a relative motion that's actually necessary in order to affect the compensation for momentum transfer, go from one to the other. And milestone 3, which is kind of like the exchange of a gamma, if you will, the line width of such a transfer is very, very narrow. So I'm curious, like in both cases, how do you compensate for the line width or even the energy mismatch of the two?
Yeah. So I don't have a plot here, like a specific plot, but just an illustration for the second part of your question. For instance, there are plenty of heavy nuclei. If you see the gray line at the top of the W excited, so these heavy nuclei have a very density, like a very large density of states in this region. So yeah, I honestly, I don't have a sensibility about how thin are these lines and how thin is the required line to be. But for sure, there are plenty of lines in there for many examples. And Peter, tomorrow, I think he has a slide with such a plots where you can really see the density of slides, of sites. While the first question was, sorry, more about the...
yeah, sort of the momentum for concerns.
That honestly, I don't know. I should think a little bit more about it. But I really think that's not very different. Like the experiment we want to do is not very different from the one that I presented to you by Chumakov and colleagues. Like really see a delocalized, like an excitation that gets delocalized thanks to this coupling by non-radiative transfer.
Okay, thank you.
Yeah, thanks.
And Nicola, we only have time for one more question, please.
Okay. Yeah.
Thank you very much for the privilege. The most likely fusion reaction of deuterium in a lattice is going to be with any residual protons there, because the PD reaction has a much lower reduced mass, and I think the enhancement will be another 14 orders of magnitude. This will dwarf any DD reaction. What do you say about that?
Can you also repeat the first part of the question?
The reduced mass of the PD
Yeah.
fusion reaction forming helium-3 should increase its rate compared with the DD reaction producing helium-4 by about 14 orders of magnitude. So it ought to dominate any fusion reaction just by the tiny amount of protons which might be present in deuterium.
Honestly, I don't know how to respond precisely to this. What I can probably comment, like as a side, maybe we can talk about it more later, is that these are thought to be coherent reactions, basically. So we cannot think about these fusion events as the fusion that we think happen like with incoherent fusion. So yeah, but maybe we can discuss more about it later. Thank you.